So as we hopefully finish up here with our last little bit of algebra or algebraic limits, how to figure out a limit without using a graph or a table, you've got to memorize a couple other two more trig tricks. Well, three, I guess, technically, but two of them are the same, and then the third one's a little bit different. So if you're going to evaluate some things with some trig functions, they're not easy to do unless you have one of three things: a calc, a smart, helpful friend, or a couple of trig limits memorized. And so the College Board expects you to memorize these trig limits. So I would start off by evaluating what's the sine of x over x using my calculator. And then after we figure out what's happening with our calculator, then we can just memorize this forever. Second table start, we're approaching 0 this time. So then I go look at my table, and what would you predict that the limit is as you come in towards x, as x approaches 0 from both sides for this function? And if your gut said 1, you would be correct. So the limit of sine x over x as x approaches 0 is 1. Now, if it was anything else or lots of different things, well, there's lots of problems. But if you're looking at some other values, you could plug those in and maybe get out an actual number like 2 you could actually calculate. But when we plug in 0, we would get 0 over 0 because sine of 0 is 0, and then you plug in 0 there. It turns out that this limit ends up being 1. And for those of you who want a picture of what this looks like, negative 10 to 10 to 1, I think it's a pretty small graph. So I'm going to go from negative 1 to 1. Let's see if that's a good enough picture. We could even go oh, there it is. So this is what the graph of sine x over x looks like. And when I trace to 0, notice there's nothing there. But the limit from either side is both approaching that height of 1. And then we're going to do the same thing here for the limit of 1 minus cosine of x over x. This time we're approaching 0 again, so I go to my table. Now what does it look like we're approaching? Negative 0.02, negative 0.01, negative 0.00. It ends up, this approaches 0. I should probably try to direct substitute first. Never not first. I plug in 0. Cosine is 1. 1 minus 1 is 0. 0 over 0. Yep, we run into a problem. Well, it turns out that there's just a hole there. So this is the way Corpy recommends to memorize it, which I like. You must memorize this. Memorize. And here's how he remembered it. He calls this sine, and then he calls it cosine. Now, it does turn out, like I said, that there's a third one, but the third one does whatever sine does. So the tangent of x over x as x approaches 0 is also 1. So tangent and sine behave the same way. So let's take a look at some tricks, some things to point out, some things to remember. What happens if we want to figure out the limit of the reciprocal? Well, what's the reciprocal of 1? It's going to be 1 again. So that's what's nice about 1 is when I reciprocal it, it's still the same thing. So I don't care if it's sine x over x or if it's x over sine x. The other thing to think about on this next one is when you've got a quantity, sine of something divided by that same something, it still is going to be 1, which it's tempting to think that it's going to be something like 5 here, but it's not. I mean, if I just said to you, let y equal 5x, then I would have sine of y over y, which would look exactly like this. And I don't think you'd have any problem saying that it's 1. The point of these last three examples, everything turns out to be 1. But the point is to emphasize this idea of sine of something divided by that same something is what this property is really saying. Now I've got this time I've got the sine on the bottom, but it's sine of something divided by that same something. That's 1. Now let's try to use that logic over here when we're talking about our cosine rules. So now when I reciprocal cosine, we run into trouble because what's the reciprocal of cosine? So 0 over 1 becomes 1 over 0, which becomes dne. So when I try to reciprocal the cosine trick, things blow up. Then we try to, okay, but here we go back to that same idea. Cosine of something over that something is the same as cosine of x over that 1 minus cosine of x over x. So this one and this one, these two things behave the same way. That gives me a limit of 0. It doesn't matter that you have more stuff attached to the x because it's the same stuff that's inside of the cosine. So I could do a direct substitute, or I could do a substitute, take it out, and put whatever I wanted in its place. So the next one, here we go again. 1 minus cosine of the same thing on the top as what we have in the denominator. Oh, I fell for it. I fell for it. Dang it. Oh, no. We're okay. We're okay. Well, wait a minute now. Oh, yeah, okay. And then here, what I'm getting caught up on, I felt like this should be like a 9 or a pi or something like that, but that's still causes a 0 here. This is -7. So when I plug in -7, that causes a 0. So we're still doing the same thing. This would still end up being 0. I mean, because if the overall limit coming from the left is 0, then just coming from the one side limit would also be 0. So let's look at a couple of these, ones that are a little trickier, a little bit more hidden. Okay, so now that we've got these trig moves memorized, we now need to apply them in very creative and clever mathematical ways. The way I recommend, or at least Corpy showed me how to do this, and I thought it was a great idea. So I need sine of 7x over, I want this to be a 7x. So what I'm going to do is I'm going to create some space for what I want. So I want the x still down there, but I don't want the 6. So I'm going to move that over here. Now I'm going to create what I want. I want this to be a 7. Now what's the price that you have to pay there? Is that I'd have to put a 7 up here. Now when I start to clean this up, what's the limit as x approaches 0 of this thing? That would end up being 1 times 7 over 6, which ends up being just 7 over 6. And so there's an extra little move if you want to memorize it. I don't memorize it because I like this technique better of building what I need. But if you want to memorize it, this is what it looks like. The limit as x approaches 0 of sine of ax over bx is equal to a over b. If you want to memorize that, you can. Sine of 7x over 6x ended up being 7 over 6. It's the same thing, by the way, with tangent. Tangent's going to behave the exact same way as sine in these scenarios. But to me, I'd rather just build it. I don't like to memorize stuff. I was never a good memorizer. I was always a better understander of what was going on, if that's even a word. So for our next one, what would this look like? Well, I'm going to set it up. The limit as x approaches 0 of, okay, I know I've got a sine of pi x on the bottom. I like the x of the 3x. I don't like the 3. So I'm going to move that over here. Now I'm going to create what I want. I want this to be a pi so that I can clean this up, and that means this is going to be pi. And then we can now evaluate this. So this turns out to be 1. This is 3 over pi. So 1 times 3 over pi ends up being 3 over pi. Is that the same thing we would have gotten here? Yes. Yes. Okay. Let's have you pause here and try to clean this one up on your own. All right, let's see how you did. So I hope you noticed that there's a 4 out in front of this. So 1 minus cosine of 11x over, take a 4 out of this. That leaves behind, oh, life is good now. Life is good now because look, the 4s are going to cancel each other out. And now I have 1 minus cosine of something divided by the same something. So those are going to reduce, and we're just left with 0. Now you got to memorize these. You got to memorize the fact that 1 minus cosine x over x ends up being 0. And then you've got to be able to recognize when to use it. All right, so on any of these, if you feel confident, you might want to pause. I don't know if I'll try to remind you to pause and try some on your own. But if you're feeling good, go after it. Okay, so my math voice here says, okay, I like sine over x, but I remember from pre-calc that I can't just break it up into its own. I've got to break them up into two separate ones. So I would get x over x plus sine over x. Now, what's the limit? Well, what's x over x? That's 1. Plus, what's the limit as x approaches 0? I guess I should do this. I didn't write limit twice, so I should really break it up. So what's the limit as x approaches 0 of sine x over x? That is also 1. 1 plus 1 is 2. So in this case, I guess I'll show you the long way, but you're going to just want to remember that this does the same stuff that sine does, but I'm going to show you really quick why. Limit as x approaches 0 of x over, now I'm going to turn tangent into its sine and cosine functions. Nobody wants to divide by a fraction, so what do we do instead? Flip and multiply. I'm going to flip this up into cosine of x over sine of x. And we're left with the limit as x approaches 0 of x cosine x over sine of x. So now we've got our x over sine x thing. What does that end up being? The limit as x approaches 0 of x over sine x ends up being 1 times, but then now I can direct substitute 0 into this. What's cosine of 0? Hopefully you remember that that's 1. So I get 1 times 1, which ends up being 1. So my point is, x over tangent x behaves the same way as sine does. So if you remember that, if I go back over here, this is what I was talking about. If you remember that sine x over x is 1, tangent does the same thing. And there's your mathematical proof why that would be true. All right, this one's a little thinker. What do you think your first move is going to be? Because we don't have any rules on secant. Well, hopefully you thought, well, if this is secant, I can at least turn it into, I need it to be either sine or cosine. Those are the tricks, or tangent. But the easiest thing to turn this into is to turn it into cosine. So that would be the limit as theta approaches 0 of 1 over cosine minus 1 over theta times 1 over cosine. Now we go back to our other techniques that we've talked about. How do we get rid of a fraction within a fraction? We multiply by the least common multiple. So cosine of theta to the top, cosine of theta to the bottom. So we would now have the limit as theta approaches 0 of cosine over cosine is 1 minus cosine over, now this is all multiplied, so you don't distribute this. Like I had to distribute this up here because this is added, subtracted. Down here, I just multiply. I can multiply it by either one of these because of the associative property of multiplication. So I'm going to multiply these two together. 1 over cosine times cosine is 1. So I'm just left with theta. And then this becomes our technique, the thing that we're supposed to memorize and be able to recognize. Oh, what did I forget to do on every single one of these? First, never not first. Plug in 0. 0 plus 0 is 0 over 0. Dang it. Plug in 0. I get a 0 on the top. What's tangent of 0? Would be y over x. Would be 0 over 1, which is 0. Secant. Oh, this gets a little trickier, but remember, secant's the reciprocal of cosine. So the reciprocal of cosine is 1. 1 minus 1 is 1. Try again. 1 minus 1 is 0. The bottom's easy because that's 0 times 1. So that's 0 over 0. Okay, next up, I'm going to encourage you to try this one on your own. I'll give you a hint. When you plug in 0, we would get sine of 0 is 0. And then I get 0 times anything, so it is 0 over 0. I'm going to encourage you to pause and try to handle this one on your own. Okay, so this is where I want to try to break this thing up. I'm going to put out front here what I want. I like sine of 5x, and I want this to be a 5x on the bottom. So I've got the x times by, now I just keep track of what else I had. I had a 4 here, and then I've got a cosine of 2x on the bottom. Okay, so I need that denominator to become a 5, so I'm going to put a 5 here. The cost for that is to put a 5 there. And now we can start to clean this up, so this ends up being 1 times, this is 4 times 5, which is 20 over, then I could put 0 in here, so that's cosine of 0. What's cosine of 0? 1, and we end up with 1 times 20, which ends up being 20. That's tough, but doable, It's not beyond your skills. You're the best of the best. Here you go again. Tangent of 0 is 0. Sine of 0 is 0. You take it from there. So I'm going to start to organize this in the things that I like. I like tangent. Tangent of 3x over is a good thing. Sine of 4x under is a good thing. Times, and I'm going to need an extra one because whatever I put here, I don't want to put it with this because it'll mess that up. So I'm going to create another fraction that I can look at to try to make it all work together. So if this is tangent of 3x, I want this to be a 3x. If this is sine of 4x, I want this to be a 4x. Okay, wait, crap. I should have done a better job of writing this out. So if I wanted a 3x down here, I needed to put a 3x up here. If I wanted to have a 4x up here, I needed to have a 4x down here to keep things balanced. And now I can start to clean this up. This is one of my trig memorizing things. Here's another one. And then the x's are going to cancel, and I'm left with 3/4. So what's 1 times 1 times 3/4? 3/4. All right, now I could show you how to do this, but if you could see it on your own, it's going to go a lot farther. So try to see it on your own. Did you see it? Hopefully. So what I did here was I said, okay, I don't want cotangent, I want tangent. I don't want cosecant, I want sine. Luckily, what's the reciprocal of cotangent? Is tangent. So I can just take this and I can reciprocal. I'm going to actually do it over here. So I can bump the cosecant to the top and it would become sine. I can bump the cotangent to the bottom and it becomes tangent. And now I can apply my two trig tricks. So I've got sine on the top over whatever. I've got tangent on the bottom. Okay, let's see. What would make the first guy happy? He needs a 25 and an x. So to cancel that out, I need a 25 and an x. And you guys, some of you are probably catching on that I'm writing that x more than I have to. I just don't want to overthink it. So I just write it in both places and cancel it out at the end. What I'm saying is, since I put an x there, I know I'm going to have one there. It's up to you if you want to see that shortcut. So this ends up being worth 1. This ends up being worth 1. This ends up being worth 25 over 11. And multiply all that together, I would get 25 over 11. Oh, try the next one on your own. You have 10 seconds. And the reason I said you have 10 seconds is because this is a direct substitute one. This is the same. X approaches 0 of cosine of 14x times sine of 9x when I bump that from the bottom to the top. Now I can direct substitute, and I would get cosine of 0 times sine of 0. Cosine of 0 is 1. Sine of 0 is 0. 1 times 0 is 0. H. Oh, H is kind of sneaky too. See how far you can get. All right, so I said I don't want to flip this up. I can flip this one down though. So I'm going to have the limit as x approaches 0 of, I've got the sine of pi x on the bottom already. And then I'm going to flip down another sine of 7x. Now the problem here is that if I put a pi x up here and a 7 pi, let me try again. If I put a pi x here and a 7x here, then I've got to put a pi x and a 7x down here. I'll do it in a light color. So if I do a pi x above this guy and a 7x above this guy, that means I've got to have a pi x and a 7x, which isn't going to fix my problem because I'm still going to have zeros on the bottom. But what I can do now is I can actually just direct substitute into this thing. So there's no nice way to clean this one up. When I direct substitute, limit, I don't like the way I wrote that. The limit as x approaches 0 of, let's say I didn't do that, and I just direct substitute, I would have 1 over sine of 0 times sine of 0, which ends up being 1 over 0, which is a VA. So I didn't direct substitute like I should have right off the bat here. I could have direct substituted, I could have got a 0 on the bottom and figured out that this was going to automatically be a DNE. Because I've got something on the top that is not 0, and I got a 0 on the bottom. Game over. Game over, man. Game over. Let's just keep plugging along. Okay. I want sine. This time I've got sine squared. That just means I've got 2 of them. So the limit as t approaches 0 of sine of 2t times sine of 2t, which means what do I want on the bottom? Well, I want a 2t underneath each one of these. Now what's nice is I've got a 3t squared, so I'm going to organize this. I'm going to leave the 3 over here, and I'm going to leave a t with each one of these. Now to make this guy happy, he wants a 2. To make this guy happy, he wants a 2. Well, if I put a 2 times a 2, I have to put a 2 times a 2 there. And we're left with 1 times 1 times 4/3, which ends up being, of course, 4/3. Now, the first time you see it, when you watch me do it, it seems like it's really easy. But I've done these problems many, many times, okay? This is the work that I've done to earn that spot. So your paper should not probably look as nice and neat as mine does. There should be a lot of erasing going on, a lot of drawing lines through stuff so that it doesn't get graded. That's okay. You got to earn this understanding. Now, having said that, you should be able to get going on this. You should be able to do J. You should be able to get a pretty good start. So pause, give it a try. Okay, so let's see how you did. So I'm going to start off by trying to organize things. So I've got 2 sines. I've got a sine of 2x and another sine of 2x. And now I know I'm going to want fractions here, so I'm going to actually bump this down here, down the line a little bit. I've got a sine of 5x, and I've got another sine of 5x. And then I've also got to come up with a fraction in case things don't all make each other happy. In case I got to add some things. Okay, so this guy needs a 2 and an x. This guy needs a 2 and an x. This guy needs a 5 and an x. This guy needs a 5 and an x. And now we can go back and see what things we need to add here to make everybody happy. So for instance, I did 2 times 2. So I need 2 times 2 up there. I did 5 times 5. So I need 5 times 5 there. And then I've got x over x. I've got x over x. So I don't need to add any x's to the mix here. And then I can just start to evaluate. So this would be 1 times 1 times 1 times 1 times 4 over 25, which ends up being, of course, 4 over 25. That's making me, wait a minute. I'm going to go direct. I'm thinking direct substitute here. I keep forgetting to do that on a lot of these. I really should, and I'm not. This is 0 over 0. Some of them are tough to direct substitute into, but the ones that are easy, I got to remember that that's got to be my first technique. Never not first. So when I get to this one, I'm going to direct substitute. Well, I'm going to clean it up a little bit first. I don't like that secant. I don't want to try to figure out what secant is on the bottom. So that's going to be the limit as x approaches 0 of e to the x times cosine squared of 8x times cosine of 4x. Yeah, life is good here, man. We don't have to, this is a plug and chug. There aren't any, we don't have to create any scenarios. So I can plug into this e to the 0 times, remember what this means, that the whole thing's getting squared, times cosine, why did I just not write 0 there? I wish I would have. So e to the 0, this is the one that I expect you to memorize. This is the only one that they expect you to know by heart. E to the 0 is 1. Just like natural log of 1 is 0, e to the 0 is 1. Cosine of 0 is 1, so that would be 1 squared. Cosine of 0 is 1. 1 times 1 squared times 1 is 1. Nice. Sneaky, Corpy. Sneaky. All right, let's finish strong here. Well, we're not finished. Maybe we can get the back done too in this video. Alrighty. Oh boy. Jumpman. I'm sensing a Jumpman here. But I also noticed that this thing and this thing are connected by a plus. So I want to break this up. But when I break up a fraction, I've got to break them up separately. So what I mean by that is this is going to be the limit as x approaches 4 from the right of tangent of x minus 4 over x squared minus 4 plus the limit as x approaches 4 from the right of the absolute 2x minus 8 over x squared minus 4. That's an absolute value there. You can do it. Pause. You can do it. Try to get the next move in. The next move's pretty easy. After that, it gets pretty complicated. Well, it's not too bad. Okay. I hope your math voice looked at this. I hope your math voice looked at it and said, I can factor that. I hope your math voice looked at this and said, I can factor that because I'm trying to make a jump man. So I've got a limit as x approaches 4 from the right of tangent of x minus 4 over x minus 4, x plus 4, plus the limit as x approaches 4 from the right, and I'm going to take out the 2, x minus 4. Oh, wait a minute here. Dang it. Dang it. I think we could have just direct substituted. Maybe not. Maybe not. Yeah, well, let's see. Let's see. This one we definitely could have, right? No. Yeah, we could have definitely. Look. Oh! Oh, I thought it was a 2. I thought it was a 2. I should have just direct substituted. Why did I do all this extra work? I'm making a jump man and oh. This should be not x minus 4, x plus 4. This should be x minus 2, x plus 2, which isn't even one of my trig tricks. I would have changed this problem if I was Corpy. I would have made that a 16. It would have been a much more fun problem. X minus 2, x plus 2, which plugging 4 into that does not create a 0 on the bottom. Dadgummit. So this becomes tangent of 0 minus, or 4 minus 4 is 0 over not 0, basically, right? So if that would be what, 2 times 6, which would be 12, plus plug 4 into this, 2 times 0 is 0 over 12 again. So tangent of 0 is 0 over 12 plus 0 over 12 is 0. Dang, nabbit. Wasted all that time. That would have been a much cooler problem. I would change that to a, if I was El Corpo, I would change this to a, but if you change that to a 2, then we don't have the, we'd have to approach 2, not 4. So I'd change this to a 2 if I was El Corpo. Anyway, beggars can't be choosers. I like his stuff, so I'm taking it. I'll take the mistakes once in a while. So this is just his list of all the things that you should have memorized. It's basically saying sine of anything over that same something or reciprocal of that or tangent, same pattern, is 1. This is the thing that he recommended memorizing. So if they're the same for sine or tangent, it's going to end up being 1. When it's m over n, what's surprising, it doesn't matter if it's on the bottom or on the top. I guess with reciprocals, it ends up being m over n no matter what. I don't think this stuff is necessarily worth memorizing. I'd rather have people understand the idea, but it's up to you. All right, let's finish this out. General cleverness. This is a great method when all else fails and you have to make a dugout canoe from a toothpick. So this is where you just try to recognize and come up with tricks. So as I look at this thing, I know that there's something with 1 minus cosine of x that's associated with x, but then I'd have an x left over, which would always make that thing worth 0. So what I'm going to do instead is I'm going to do, I look at this and I think conjugate. I don't know how to teach you to see that, but when I see 1 minus cosine, I think of 1 plus cosine. So when I times by 1 plus cosine of x over 1 plus cosine of x, I get 5x squared times the quantity 1 plus cosine of x over 1 minus cosine of x squared, cosine squared of x. Now, do you see something here? I see it. I don't know how to get you to see it. I see it. This becomes the limit as x approaches 0 of 5x squared times 1 plus cosine of x over sine squared of x. You remember that from your trig identities. Now I can organize this as a sine squared over an x squared, or a sine over an x, with my trig tricks. So that's the limit of. So I'm going to take the x over sine x times another x over sine x times a 5 times the quantity of 1 plus cosine of x. So see what I did there? I took one of these x's with one of these sines. I took one of these x's with one of these sines. And then I started to just clean that up. Now I can do my trig trick. 1 times 1 times 5 times the quantity 1 plus cosine of 0. Cosine of 0 is 1. 1 plus 1 is 2. 2 times 5 is 10. I get it. I know that feeling that you're feeling right now. How did you see it? How do you recognize these? And it just comes with practice. So this is the first time that you've seen it. Just like a couple years, 20 years ago was the first time I saw it. And then the more you see them, the more likely you're going to be able to use them. This is another one that who would have ever thought that you could do this? But this turns out to be, if you try to factor this thing, let's do a quick factoring. Go ahead, I'm trying to kill some time here while you factor this. How does this factor? X and x, minus 5 and minus 5. Well, it turns out then, this is x minus 5 what? Squared underneath a square root. Now, you might be tempted to say, well, I can square root, they would cancel out, and then I can start to reduce here, but it gets a little bit trickier than that. Because you're applying the squared first, this is essentially saying, this is the equivalent of saying the limit as x approaches 5 of 3. I'm going to factor out the 3 on the top. Now, you would never know this. You would never know this. I get it. I get it. I get it. So this is me teaching it to you or showing it to you for the first time. So the absolute value of a minus b is the same as a minus b getting squared and then square rooted. Now you might say, well, wait, don't those just cancel each other out? They do after you take into account that if this is ever negative, it gets squared out to become a positive and then gets square rooted again, which means that these are always positive. So both sides of this always ends up being a positive. This always ends up being a positive. These are equivalent ways to think of each other. So whether you see this or not, this is a Jumpman scenario. So this ends up being a DNE. Because we're approaching the limit from both sides, this would be a DNE. This is a Jumpman. I'm going to highlight that. Jumpman. Now, how would you know that? From both sides. You wouldn't know that until now. And now when you do these problems, you should try to recognize that. So let's just double check. Let me prove it to you. I'm going to take my original function, which is 3x minus 15 over the square root of x squared. Subtract 10x plus 25. Our table, we're approaching 5 from both sides. So if we look at our table, one side is approaching negative 3, the other side is approaching 3. This is a DNE. We've got to jump. Jump, man! All right, you look at part C. I haven't been doing a very good job of plugging in to make sure that it equals 0 first. So let's do that here. So I plug in 0. Tangent of pi over 4 is 1. That's where the cosine and the sine are the same value. So 1 minus 1 is 0. Sine of pi over 4 is square root 2 over 2 minus square root 2 over 2. That ends up being 0 as well. So what's the technique here? What would you see? I tried a bunch of different stuff my first time doing this. And if you look at my notes here, I went a bunch of different ways. I tried to do the conjugate. I ended up doing the conjugate at the top. I tried to do the conjugate at the bottom. And then I thought, well, wait, what is tangent? Tangent is simply sine over cosine. And now that I've got sine over cosine, I can try to clean up that fraction. And what would you multiply by to kill off that fraction? Well, you would times by cosine of x to the top and cosine of x to the bottom. Now, be careful here. This is a distribution scenario. So you've got to distribute this into both of these. So the limit as x approaches pi over 4, cosine times 1 is cosine, minus cosine cancels in this case, and we're left with sine, over, now I get cosine times sine. Oh, actually, no. What I can do, I don't want to distribute this, because I would just end up factoring back out anyway. Look at, why is your math voice kind of happy? Do you see it? Those are close. Those are close. What are they off by? They're off by a negative. Remember that this one is negative and this one is positive. You got them mixed up. So what I can do is I can factor out a negative 1, which would make the sine x positive and the cosine x negative. And now I can cancel them out. So now I'm left with a negative 1 over cosine of pi over 4, which turns out to be negative 1 over root 2 over 2, which turns out to be its reciprocal, which is negative 2 over root 2. Then you need to rationalize it, times by root 2 over root 2. This is all pre-calc stuff, that's why I'm going kind of quick here. And what would we be left with? We'd have a negative 2 root 2 over root 2 times root 2 is 2. Those reduce, and I'm left with negative root 2. Woo! What's the big idea from this one, though? The big idea is right here. This idea to think that I can turn tangent into sine over cosine. And sometimes you try a bunch of different things until you get to the right spot. That's the way it goes. Here's your alpha plus beta formula. Pop quiz. See if you can do it at the bottom here. Sine of alpha plus beta equals. Pause it, go. All right, so this is how I memorized it. Sine starts with sine. And then sine switches. So it switches to the other thing. So it's sine alpha, cosine beta. If these two things switch around, then this doesn't switch around. So this would stay as a plus. And then you do the ones you haven't done yet. Cosine of alpha, sine of beta. Let's say that you're going the other direction. Let's say you're doing this now for cosine. Cosine of alpha plus beta. Pause on your own if you think you can do it. If not, I'll help you remember it. Or I'll help you try. This is the way that I remember it. Cosine starts cosine. Cosine starts cosine. Sine starts sine. But sine switches. So cosine doesn't switch. So it stays as beta. Now, if these two don't switch, then these two do. The sign in the middle does. You see what I mean? Either these change or the sign in the middle changes. And then you just remember to do the things you haven't done yet. Sine of alpha and sine of beta. Now, if this becomes a negative, then that becomes a positive. If this becomes a subtract, this becomes a subtract. This becomes a subtract, that becomes a plus. So let's apply that now. Let's have you do your sine of alpha of a sum on that first piece. So that would be the limit as h approaches 0 of sine of alpha switches to cosine of beta. Since that switch, this stays the same, and then we do the ones we haven't done yet. Cosine of alpha, sine of beta, minus sine of x, all over h. All right, so my math voice at this point would notice that I've got nothing in common until I get to these two signs. That's the only thing I have in common. So my math voice would just say, get those together. So I'm going to actually break it up into two fractions. The limit as h approaches 0 of sine x cosine h minus sine of x all over h plus the limit as h approaches 0 of cosine of x sine of h all over h. Since these both have a sign, I can factor out that sign. The limit as h approaches 0 of sine of x times cosine of h minus 1 over h plus the limit as h approaches 0 of cosine of x sine of h over h. All right, do you see it now? I know there's a lot of tricks and backflips and stuff that happen from there, but can you see it from this point? Yeah, I would say that hopefully at this point you see this pretty well now. So these are those trig tricks. So now I can direct substitute into this. I wish I would have written that over here so I'd had just a little bit more room, but I'm going to have to squeeze it over here. So now I can plug in 0 for h. This, though, and this, though, fit into our trig memorizing things, our trig identities that we're supposed to have memorized. So it doesn't matter if it's 1 minus cosine or cosine minus 1, because all that would do is give you a negative, and the opposite of 0 is still 0. So I don't care what order this is in, but I know that this thing ends up leveling off at 0. So I'm going to have sine of x times this thing levels off at 0, plus cosine of x doesn't care what h is, times this thing levels off at 1, which I can then clean up. That's 0. Cosine times 1, that's cosine. Nasty. Crazy. Difficult. Hard to remember. How would I ever know how to do this on your own? You don't. That's why you've got to be shown it, and then you start to come up with it, and then you start to remember a little bit, a little bit, a little bit. Direct substitute. That'd be 1/2 squared. That'd be 1/2 squared would be 3. That'd be 1/2, that's 1. 3 plus 1 is 4. That'd be 1/2, that's 2. 2 minus 2 is 0. All right. Now, you should see the first move on the top and the first move on the bottom. Don't overthink it. Notice it. I know I've got a hole in here, and I've got to figure out where that hole is. But there's a real nice, easy technique on the top, and what do you notice? They're all divisible by 2, right? I can divide out a 2. So I can take out a 2. That leaves behind 6 cosine squared of x plus cosine of x minus 2 over, I could take out a 2. That's 2 cosine of x minus 1. So life is good. Guess what's happening to those 2's? They gone. Math voice. Factor. And you know what? I bet you this is going to be one of the factors. Call me crazy, because I know that when I direct substitute, I end up getting the 0. So this is going to be one of the factors. We just got to figure out what the other factor is. The limit as x approaches pi over 3 of. Okay, now I'm going to factor things with cosines. So I'm just going to put cosine x in there instead of just x. I've got to do factors of 6. That's going to be negative 12. That make 1. So that's 4 and negative 3. So I need a 4 and I need a 3. So the 6 has got to break down into a 3 and a 2. The 3 is going to make the negative 1. The 2 is going to make the positive 4. There it is. They gone. Now I can direct substitute. 3 cosine of pi over 3 plus 4 cosine of pi over 3. If you go to your unit circle, you draw your triangle, that should be 1/2. So what that, why did I write plus 4? Should be a 2. This should be a 2. This should be a 2. My bad, my bad, my bad. That should be a 2. Because, right, 2 times 2 is going to make my 4. I just thought it made the 4 right there. 2 times 2 makes the 4. Take away the 3 is the 1. So then that'd be 3 times 1/2 plus 2. 3 1/2 plus 2. That ends up being 4, so that's what, 7/2? Crazy. Crazy. These are crazy. They're crazy. But the more you see them, the more practice you do, the more we talk about them in class and in notes and then through the quizzes, and that's what gets you ready. That's how you'll start to recognize them on your own. So, good luck.